Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, thank you very much for that kind introduction, and also thank you very much for inviting me to give the talk here today. Today I'm going to be talking about some work that we've been doing on applications of submodularity in speech recognition and natural language processing. This is primarily going to be an empirical talk. It's going to talk about practical uses of submodular functions. What I'm not going to talk about are some of the algorithmic characteristics of the procedures that are used to actually do the optimization necessary for submodular functions' use. So as an outline, first, just in case there is some uncertainty about the definition of submodularity, we'll briefly review that and at least get an intuition as to why they're useful as a model for a variety of problems in speech and language. And then we'll talk about a number of different applications that we've done in using them for things like document summarization and also for data summarization. When you have large data sets, how do you summarize them with minimal distortion in a variety of different settings, including both speech recognition, statistical machine translation, and also this is not a computer vision session. I'll give one additional application in image collection summarization. So this is each one of these topics, I should say at the outset, could easily occupy a half-an-hour talk. So I'm unfortunately inevitably going to have to skip a lot of the details of these presentations. In fact, I've already shortened it quite a bit from what I had originally wanted to present. But if there are any questions at any time or at the end, please feel to ask me, and I can provide you with whatever details you're interested in knowing. And then lastly, in terms of the introduction, I'd like to acknowledge a number of colleagues and students I've worked with on this work. Okay. So first of all, what is submodularity? And why do I think of it as a generalized form of independence or complexity measure? We can just look at the definition of submodularity. So submodularity is a function on subsets of some finite set. So V is a finite set, and 2 to the V is all subsets of the set. And a submodular function is defined on any subset. It provides a value for any subset. And the function is submodular if it's the case that for all possible subsets, it satisfies this particular inequality, which to some of you might look like a sort of a discrete form of concavity. Perhaps an equivalent definition that's perhaps more intuitive to some of you is the notion of diminishing returns. And that basically says that if you consider the submodular function as a valuation function, that basically anything that you don't have becomes less valuable as the context in which you consider it grows. And so the context in which you consider it is either A or B. So B is the larger context and A is the smaller context. And V is something that you don't have. And this is the incremental or the marginal gain of V in the context of A. And that's larger in the smaller context than V is in the larger context. So B is the larger context. So that's the definition of submodularity. So this is the notion of diminishing returns, that the more you have, anything you don't have becomes less valuable when the submodular function is sort of a value-based, measures value. So here's an example of submodular functions that, there we go, there's the example. So a very simple example is balls and urns. So imagine that you have a large number of balls and you measure the value of the balls based on the diversity of colors. So in this particular case, on this left urn, the value is 2 because you have 2 different colors, and it doesn't matter how many balls you have. What is important is how many colors you have. And in this particular case on the left, when you add this blue ball, you increase the value by 1. And if you add more green or more red balls, the increasing value doesn't decrease. I mean, it doesn't increase. It can only decrease in case if you ever happen to add a blue ball, then adding a blue ball to an urn with blue balls already in it makes that additional blue ball have value 0. So that's the notion of diminishing returns, and that's therefore a submodular function. This is a classic submodular function that's useful for such contexts as defining what submodularity is. Now, discrete optimization, why do we care about submodular functions? One is because that they're useful models for a variety of different domains, and they've been useful for historically in operations research, in combinatorial optimization, in economics, in game theory, and in pure mathematics. And more recently, they've become of interest in machine learning, maybe in the past decade. And even more recently, they've started to become of interest in some of the applications of machine learning, like speech and language. And so why do we care about submodular functions? Not only are they potentially a good model for a variety of domains, but also because they're amenable to fast optimization in many cases, or fast approximate optimization with guarantees. So here we're given a finite set of objects V. And 2 to the n are all possible subsets of that finite set. And so A is a particular subset. And we have some function which judges the quality or value or cost of each possible subset. So f of A is some real number. And so 2 possible optimization problems we might be interested in are, this is in the unconstrained form of optimization, is basically just finding the minimum subset, the subset that has minimum value, or finding the subset that has maximum value. And if f is arbitrary, if the function is arbitrary, then these optimization problems are hopelessly intractable and in fact inapproximable. But it turns out that when f is submodular, that equation 3 can be done in polynomial time. And in fact, oftentimes for certain submodular functions can be done in very, very low order polynomial time. And then equation 4 can be done approximately well, with constant factor approximations, also in low order polynomial time. So submodularity basically renders these 2 optimization problems not only possible, but also feasible and practical for many problems. So this is potentially useful. Now, another form of optimization is when you add constraints, discrete constraints. So here, basically, let's say we're only interested in a feasible set of possible subsets. So script S is the feasible set. And what are some possible feasible sets? Well, they might be of the form of cardinality constraints. So we're only interested in sets of a given size. Or maybe we're only interested in sets of a given cost, where W is some cost vector which measures the cost of each individual element in the set. Or the set S could correspond to various combinatorial objects, because let's say V is a set of edges in some graph. Then the feasible set could correspond to trees or matchings or paths or vertex covers and cuts or any combinatorial object which you might imagine being of use. Or even more interestingly, perhaps, S might actually be level sets of some other submodular function or some other function. Like, for example, S might be, the feasible sets might be those S such that G, where G is some other function, G evaluated on S is no greater than alpha. And so we have these different optimization problems. These are constrained optimization problems. And again, without making any additional assumptions, these optimizations are hopelessly intractable and hopelessly inapproximable. But when F and G are submodular, they're often solvable, and again, low order polynomial time, oftentimes with reasonable approximation guarantees. And so a lot of the work that we've been doing in the past few years has been on algorithms for doing this. In particular, for example, when the feasible set does correspond to level sets of some separate submodular function. So that was some work we did last year. But I'm not going to talk at all about that. I'm just instead going to talk about the usages of equations 3 and 4 and 5 and 6 for speech and language processing. So submodularity is useful as a model of a physical process. That doesn't mean that submodularity necessarily truly exists, but it is a useful model. And the meaning of the function, of the submodular function, depends on whether or not maybe you're interested in maximizing or minimizing it. For maximizing a submodular function, typically what one uses a submodular function for is for models of diversity or coverage or span or information. And then for minimization, oftentimes one uses submodularity as models of costs that have a cooperative nature, where if you choose one item, then the cost of another item lessens, or complexity measures, or roughness measures, or irregularity measures. Submodularity is useful for either of these contexts. And so in speech and text and NLP, basically you use the submodular function depending on whether or not you're interested in, say, minimizing cost or maximizing diversity, or sometimes both. So a function that perhaps everybody is familiar with is the entropy function. And the entropy function is a classic example of a submodular function. And the reason why I think this is an interesting one is because Shannon, in his famous 1948 paper, sort of defined a set of properties of what one wants to have for an information function, and then came up with the entropy function, which is defined based on a joint probability distribution over a large set of random variables. And here, the entropy function is seen as subsets of random variables. It's not like a parameterized by the distribution, but given a fixed distribution, entropy seen as choosing subsets of random variables is a submodular function. And that is, as you all know, a classic instance of an information function from the Shannon perspective. But there are many, many other submodular functions that are submodular. In fact, submodularity is a vast class of functions. They live in a cone with 2 to the n degrees of freedom, and including things like set covers and graph cuts and bipartite neighborhood functions and sums, the closed-end or concave mixtures, and so on and so forth. So there's a very large set of submodular functions. But in each case, what it turns out to be interesting is that they can all be seen as essentially forms of Shannon information functions without necessarily them having the difficulties associated with the entropy function. Because even, for example, querying an entropy function itself can just itself take exponential time, because you need to do a probabilistic inference problem to get an entropic query. And you could essentially make additional structural assumptions about the probability distribution to make the entropy query tractable. But doing that sort of presupposes the very structure that you exactly want to be able to discern based on using the entropy itself. So that's a chicken and egg problem, which we can't solve. But what we can do is instead use other forms of submodularity as information functions. And we avoid this exponential query cost problem, because not all submodular functions, in fact, most submodular functions don't have this exponential query cost problem, like graph cut, for example. So that basically means that any submodular function defines some sort of abstract, in some sense, combinatorial notion of independence. And so based on the submodular function, you can define independence, abstract independence, based on additivity, or conditional independence based on another form of additivity, or strict dependence based on there being a strict inequality in this equation, or notions of sort of combinatorial conditional mutual information, and other notions of information amongst sets of sets in equation 11. So then the question is, in all of these applications which I'm about to talk about, how do you actually find a submodular function? There are generally 2 approaches. One, which is based on sort of heuristics, where you design a submodular function by hand based on perhaps knowledge of the domain that you're working in. And you acknowledge that it's a surrogate function, that you're optimizing a surrogate, but it often, hopefully, if you've designed it well, will work for a given domain. But a more recent and promising approach in the machine learning community is to actually learn the submodular function in some way or another, or at least learn within subclasses of submodular functions. So based on data, learn the function automatically. And so I'll present results in both of these cases. So the first result, which at this point is now a couple of years old, it's about 2 years old now, is in the context of extractive document summarization. And here, so first of all, why is submodularity a useful model for extractive document summarization? Well, in document summarization, the problem is basically you've got a large collection of documents, and you want to choose a subset of the set of sentences that somehow represents the set of documents that you start with. And so here the idea is that on the left, we have one possible summary, which is green, and we're considering adding the blue sentence, and we're wondering how valuable is that blue sentence in the context of this green summary versus the context on the right, where we've got a larger summary, so there's more green, and we're considering adding the blue on the right-hand side. And chances are that if you're considering adding the blue sentence to a larger summary, what that blue sentence provides in terms of its information content is more likely to be redundant in the larger context than in the smaller context. And that's exactly the property of submodularity. So with that realization, we thought, well, maybe submodularity would be a useful model for extractive document summarization. So then we looked at the literature, and in fact, we found that unbeknownst to the authors that were actually doing this work, submodularity had been implicitly used. So is that 5 minutes in or 5 minutes to the end? 5 minutes to the end. OK, so this is really a short talk. So anyway, I will skip all of this stuff. We found that submodularity had been used implicitly, including, for example, the metric that people have used to measure the performance of a given summary, the Rouge measure, which had been developed by linguists as a way of measuring automatically without additional human intervention how good a given summary is. That turns out to be a submodular function. So we then proceeded to define a class of submodular functions. These are just different submodular functions that we used, including various mixtures. And we also learned mixtures of submodular functions in a max margin framework, which the details of which I can't go over because we don't have time. And we evaluated it on a number of different standard document summarization corpora provided by NIST. These are the document understanding conference corpora, DUC corpora. And there's 4 of these corpora. And we used Rouge, which is that measure that I had mentioned before, as an evaluation strategy. And we found that basically by using smarter and smarter strategies for constructing submodular functions, the approach worked better and better. This was the best system in 2004, and this was our work progressively over the years. And as far as I know, these results on the right from 2012, in each one of these corpora still stand as the best results ever reported on all of these corpora. So this is for DUC04, DUC05, DUC06, and DUC07. So this sort of suggests that, that submodularity is quite natural for extractive document summarization, and perhaps one should, when pursuing extractive document summarization, see it as a submodular design problem. So the next thing I want to talk about is data summarization. So here, basically, we've got this, people have talked a lot about the big data problem, or maybe the big data blessing. And the old adage goes something like, there's no data like more data. And I think I'd like to sort of turn that expression around and say, in fact, it's not that there's no data like more data, but rather the issue is more data is like no data. And the reason for more data is like no data is when you start looking at these training curves. Basically, as the amount of training data in a machine learning system increases, you start getting a diminishing returns. So this is some slides that I stole from Andrew's machine learning course from 2011. But it turned out it was very easy to find these kinds of slides because if you look around on the web, there are lots of people who've shown that as you add more data, you start getting the saturation effect, where at some point or another, more data doesn't help any longer. And so this seems to suggest that there may be a submodularity of some form going on in the training data issue. So this is exactly the diminishing returns problem. The more you have, the less valuable is anything you don't have. And for very, very large, complex machine learning systems, like deep models that everybody's been talking about recently, or support vector machines, basically this is bad because, I'm going to skip this slide. It's bad because you're spending a lot of time training on data redundantly. You're wasting your time on data that is already being expressed by other data. And perhaps the goal is to choose a subset of that data and then with minimal loss. So this is really the key question. Can statistical predictions be made more cost-effective with smaller data sets? Now, cost-effective doesn't mean necessarily that accuracy doesn't go down. It means that you have a much smaller data set and the accuracy goes down minimally. And so we did this in the context of speech summarization. And so here, basically, the problem is in the context of speech recognition, how do you choose a subset of the training set in an intelligent way and train on that? And I think I've already said this, but let me just give you a couple of facts about this. So we tried this on some fairly standardized speech recognition corpora, switchboard and switchboard cellular and Fisher data, which is fairly large vocabulary, fluent, spontaneous speech recognition corpus. And we found that this to be somewhat true in that data, but my guess is that when you look at, for example, the corporate world who have training data sets that are much, much larger than what exists in the academic world, that this redundancy problem would be even more acute. And very briefly, here are some results. So what this is showing is the top table shows a Gaussian mixture-based speech recognition system, and the bottom table shows a deep neural network-based speech recognition system. The right-hand column shows the word error rate using 100% of the data in both cases. You can see that the deep system does better than the Gaussian mixture system. And this is showing various different subsets chosen either by random subsets and plus standard deviations. There's an existing approach in the speech recognition literature called the histogram entropy approach, which is a non-submodular approach, which gets these results. And then there's various different submodular approaches. Here's one of them. And you can say that in each case, the submodular selection does better than any of these other approaches in choosing the best data set. And I thought what was interesting about this is that if you compare this number, 29.3, to 31.0, it's basically saying that a deep neural network system with only 10% of the data does better than a Gaussian mixture system with 100% of the data. So from the perspective of doing rapid development of deep neural network system models, maybe you could choose this 10% and get maybe a factor of 10 speed up in trying how many layers you want or how wide it is or what type of nonlinear you want to use. All of the kinds of things, the design decisions that one needs to do when designing a complex system, you could iterate over that 10% and more rapidly get a good solution than one would get if one was to use 100% of the data. So we also looked at this from the context of machine translation. And again, very similar to document summarization, we found that many people in the past have actually inadvertently used submodularity. And all of these references, including some very recent ones, and some quite elaborate and intricate methods, actually turn out to be submodular optimization problems. And so what, including the classic one by Moore and Lewis, which actually turns out to be a modular optimization problem. So it's in some sense weaker than submodularity. And so what we did is we approached it directly using submodular functions. And the class of submodular functions, which I don't have time to go over, is basically a sum of weighted concave functions over modular functions. And this is a class of functions that I think is particularly well suited to natural language processing, to the natural language processing community, because there's been so much work on feature engineering in this community. And so here, basically, the idea is that you have a sum of terms over the set of features of a given object, and you have weights of features and then concave functions over modular functions. And this basically says, this sort of weighs the set for this particular feature. So the results are based on are quite nice, I think. Comparing, again, random with standard deviations or the cross-entropy approach, which is what the method that most people use. And these are various different submodular systems showing that they do far better than the other baseline approaches. So I'm going to skip the image summarization because I think I'm running out of time. But I just wanted to say that we've also applied this to image summarization problems and also developed a new strategy for learning submodular functions. And the approach works very well for image summarization as well. So there's also two other pieces of work that I think are worth mentioning. So we approached the alignment problem in machine translation as a submodular optimization problem, which generalizes bipartite matching. And that also improved results. And then lastly, class-based and factored language model construction based on word clustering using balanced submodular cuts. And that was also something that achieved good language model perplexity results. That was some fairly older work. But there are a lot of applications, and I sort of foresee that submodularity can potentially be useful for natural language processing applications into the future. And here, what I presented was a few of them. And also, as an advertisement, there has recently been a couple of tutorials on submodularity, both of which are available as videos. So if you're interested in some of the more theoretical aspects of submodularity, there's this NIPS tutorial, which occurred last December in 2003. And then there's the machine learning summer school tutorial that occurred a couple of months ago, which talks more about some of the applications of submodularity in machine learning. So that's the end of the talk. Thank you very much.
Yeah, just a short comment on your sort of philosophy of more data is like no data. I think the deep learning will argue that the reason why you get diminishing return is because your model isn't deep enough, isn't big enough, at least for speech.
Yeah, so I mean, what the question was that one should also include the complexity of the model in looking at those kinds of plots. And it may very well be the case that what's being saturated is not the information that exists in the data, but what is saturated is the capabilities of the model. And I think that's right. I believe that is true. And in fact, we've done some experiments precisely on that, where we've sort of done the reverse. We've limited the model's complexity specifically so we could understand the saturation effect. I do think these things are intertwined. However, that doesn't mean that there isn't a redundancy problem in the data. No matter what the inherent complexity of the model is, what the capacity of the model is, there's also going to be a redundancy in the data. These things are mixed together, but there is a separation. There is a redundancy in the data. And if we can actually choose the non-redundant data set, we're not wasting our time on the redundant part.
So I think in the interest of time, we're going to have to hold further questions for when the session is over. I think Jeff will be around at lunch and we can all ask him questions then. Let's thank the speaker again. Our next speaker is Chris Manning. Chris is a professor of computer science and linguistics at Stanford University. He's a fellow of the ACM, the AAAI, and the ACL. He's literally written the book on natural language processing and information retrieval. I think many of you probably use his textbooks in your courses. He's done seminal work in statistical parsing, computational semantics, computational pragmatics, and hierarchical deep learning, and he's going to talk about these subjects today.
Thank you. Good morning. Artificial intelligence requires that we can create computers that have the knowledge that human beings have. And the primary place that computers can get that knowledge is from texts. So for humans, that at some point humans were able to evolve language, and that gave us a crucial advantage of being able to communicate among each other, and that led to the general ascendancy of human beings. But even after that, it was really a very short period ago that human beings developed written languages, and that provided the ability to communicate ideas across great distances and across times. And it was really that development that meant in an extremely short period of time, just several thousand years, we could move from Bronze Age technology to the kind of smartphones and tablets that we have today. And so the question now is, how can we get computers to be able to read and understand all this knowledge? The initial attempts to do that were for human beings to attempt to write down grammars and lexicons for human languages in esoteric formalisms, and to use those to be able to build parse structures for sentences. This never worked very well. Human languages are too vast, they're too ambiguous, and their interpretation is too context dependent. And so that led into the idea of maybe we could use this vast amount of text in a second way. We could also use the vast amount of text as a way to learn languages. And sometimes that's just using the vast amount of text by itself, but sometimes, in fact quite often, it means that we are using the knowledge of human beings to annotate the text in various ways. So here, this piece of text has been annotated with part of speech tags for each word. And so this led into the development in the late 80s and 1990s and 2000s of statistical or probabilistic approaches to natural language understanding. And these were incredibly successful. So by putting probabilities over things like how likely words are to follow each other, or how likely words are to get different parts of speech in a certain context, this led to all of the good tools that we have today: speech recognition, context sensitive, spelling correction, question answering, machine translation. So that was a great advance. But nevertheless, there was a big limitation to what was done here, that although we had continuous real numbers representing the probabilities of different events, we were still building these models over exactly the same symbolic representations that were used in the rule-based systems for natural language understanding. So why was that a problem? If you just look at a symbol like motel, it doesn't really look problematic. But if you think about that in machine learning or statistical terms, what we end up doing is turning this into a huge feature vector where we have a position for every different symbol. And so there's one position where it's the one for motel. And these vectors grow very large. By the time you go to web scale, corpora, they might be vectors that are millions long. But it's not really the largeness by itself that's the big problem. The big problem is that these vectors give us no representation of meaning relationships between words. So if we have representations for motel and hotel, they just have a 1 in some different position, and they have no inherent similarity. Their similarity is 0. So that's been a big problem for progress in combating the sparsity of language. And so a lot of work in the last decade has then focused on how can we get meaning representations of words that show meaning similarities. And the primary method by which that has been done is to use word distributions. So here we have the word linguistics showing some contexts in which it's appear, and we use those contexts to induce a dense vector-based representation of the word. And these models are very successful, so that if we take these kinds of models and then look at the position of different words in a vector space representation, they do a very good job at capturing similarity relationships between words. There are many methods that have been used to do this, but I just want to spend a couple of minutes telling you about a new way that we've developed in our lab, primarily by one of my postdocs, Jeffrey Pennington. And the idea of this method is to develop a new method that uses global statistics over a large corpus of text to induce word representations. And the idea is that if we look at a word and the probability of other words appearing in its context, so for ice we might get large probabilities for both solid and water, whereas for steam we might get large probabilities for gas and water. So the difference between large and small by itself doesn't indicate the difference between ice and steam. But if we take the ratio between the two of them, we then get a dimension of meaning, that we have a large-small contrast between gas and solid that represents the meaning difference between ice and steam, whereas for either a meaning component that they share like water or for some other random word, it approximately cancels out to 1. And this actually works. So if we plug in the counts from Wikipedia, you can see that this roughly gets the kind of effect that we want to get out of that. Okay, so that's basically the model, which we're calling the glove model. So we want to learn a model so the dot product between words is approximately equal to the log probability of one word appearing in the context of the other. And then if we do that, precisely vector differences correspond to this ratio of probabilities. And so essentially we're training the model to try and get these things equal, with one extra aspect in it here, which we're scaling by the probabilities of the co-occurrence. How well does that work? Well, here are the words that are closest to the word frog in this space, and the first and the second one look really good. About at that point, my knowledge of biology fails, but it turns out that all those words I'd never heard of are also frogs, including this beautiful Australian tree frog in the top left. Okay, so there are other methods of doing this. One of the recent methods that's attracted a lot of attention is the work at Google on the SIBO model. And a lot of these methods have been evaluated using a word analogy task that was developed in Microsoft last year. So the SIBO method, if you use large dimensionalities and large corpora, does a fairly good job at working out word analogy tasks. If you make the dimensionality bigger and the corpus bigger, it starts to do an even better job at working out these similarities. But we've actually, with this glove method, it's getting significantly better results, again, than the word-to-vec model. What can you do with these kind of word representations? Many things. They're very good for lots and lots of natural language tasks, but I thought I'd just mention one of them. So this is some recent work from Jacob Devlin at BBN in making use of these distributed word representations in machine translation. And so the idea in machine translation is we want to be starting to build up the translation of a text, and we want to do that in a way that's sensitive to the preceding words that we've generated in the translation and depends on the source language translation. So we'd like to work out the probability of generating the next word of the translation based on preceding words in the translation we're building up and a big window of source context. The problem is that this is basically impossible to do making use of categorical symbolic representations, because you're just killed by the sparsity, that if you're trying to represent these all as these one-hot vectors, you can't possibly condition on that much text, even if you're building models over billions of words of text. But if you use distributed representations, because they give you a wonderful ability to share meaning components, then you can. And so here are some results from this model. So BBN has a very strong machine translation system. In the 2012 NIST OpenMT evaluations, they were in first place with a blue score of 49.5 for Arabic. Since then, they've improved it a little bit to 49.8. But adding in this kind of bilingual neural network language model gives them a very large, significant increase in the quality of the machine translation system with just this one change. Indeed, if instead you consider having more of a baseline MT system of the kind that we talk about in class or something, and the only thing that you add to it is this bilingual neural language model, it gives you an increase that takes you up essentially to the level of all the other things that have been done over the decades to make machine translation systems better. So those are very significant advances. But we don't only want to understand the meaning of words. We want to go on and understand the meaning of sentences and texts. And one of the ways that we understand the meaning of sentences is by putting over them this kind of dependency grammar pars, where when we have a verb, we're looking at its arguments of its subject and its object argument, or for the object, it's got an adjective modifier. And this kind of representation is being increasingly used for a lot of semantic representation in natural language processing. And I just want to put in a little advertisement for a moment. Of course, we don't only want to do this for English, and something I've actually been very involved in the last year is trying to develop common dependency representations that build on our Stanford dependencies representation across different languages. And if we can do it with the same dependency conventions and the same label set, that allows cross-language comparison and doing tasks like translation much more easily than when we have incomparable resources. So I'm very interested in developing that effort. But if we go back to this picture, here we have words, for which I've just proposed a distributed representation, but we also have part of speech tags and these grammatical relations. And if we do nothing else, they're still symbolic categorical representations. So an interesting question is, well, can we extend things further? Because we also have similarities in parts of speech between singular nouns and proper nouns, or common nouns and proper nouns. We also have similarities between some of the relations. So we could hope to embed all of those in distributed representations. And so this is a dependency parser that's been developed recently by Danchi Chen in my group, and that's precisely doing this. So at any point in the parse, we've got a partial representation of the sentence that's been built. We're considering how to add extra words, and we're projecting all of that into a distributed representation of all of words, part of speech, and grammatical relations, and then putting that through a deep neural network with a novel activation function, and to predict the next step in the parsing. How well does that work? So in dependency parsing, there are two primary methods that have been used. There have been transition-based shift-reduce style dependency parsers, which are by far the most used, actually, because their great property is that they're really fast. So if you want to be doing web-scale parsing, that's just what you want to use. There are then graph-based parsers, which are minimal spanning tree style algorithms, which have tended to work a little bit better, but have tended to work about 2 orders of magnitude more slowly. So the wonderful thing with this parser is you can have a transition-based parser that works basically as well as the best-known graph-based parser, but it works actually not only with the speed of a transition-based parser, it actually works faster than most transition-based parsers. And the reason for that is in the categorical transition-based parsers, it turns out that really the feature computation dominates the computation time, and therefore you can do that more quickly with the dense distributed representations of a deep learning dependency parser. Okay, so that gives us some structures for sentences, but we want to go on beyond that and do more for representing and working with the meaning of sentences. And there are several ways that you can go about doing that, and there are different ways that we've worked with. One way that you might want to ground the meaning of sentences is to make use of multimodal forms of learning, and so relate sentences to pictures that show the same events. And an appealing way of doing that is to take pictures and embed them in a distributed representation. And then what you want to do is have sentences with the same that describe the picture being placed close by in the same vector space representation. And so this is something that Richard Sosha and colleagues, including me, have been working on recently. So the basic idea is this. So for the picture, we run it through the kind of convolutional deep learning analysis that's become very common in recent image processing work, and which I'm not going to describe any of the details of right now. For the sentence, we build a dependency parse using the kind of methods just described. And then over this dependency parse tree, we build up recursively a compositional meaning representation of the sentence. And then what we'd like is for those two things to be equal. And then in the typical fashion of neural network models, when they're not equal, we're then backpropagating the errors, the differences between the two, into the two halves of the model and iterating over that until they become more similar. So in just a fraction more detail, for working out the language representation, the dependencies give a tree structure. And so what we're doing is working out compositionally meanings for sentences. So when we have at night, we're starting off with word representations, and then we're building representations for phrases. And we're doing that by taking each word vector or previous lower child vector, multiply it by a matrix that encodes the grammatical relation, and then superimposing those vectors on top of each other. Okay, how well does that work? We've been able to test this with a small data set put together by Julia Hockenmeyer and colleagues, which is 1,000 images with 5 descriptions of each like this. This is only a really small data set. I imagine you could get considerably better methods with larger data sets, but this is what we've done at the moment. But if we show a picture and ask for a description, these are the kind of results we get, some right, some wrong. But I think this is already interesting and showing the power of dependency representations. So earlier we'd worked with some other kinds of constituency parse representations. It turns out on this task, perhaps because of the limited amount of data, they actually perform worse than using a bag of words representation that doesn't model any of the sentence structure of the sentence. But because dependency trees give a very direct representation of sentence structure, that model performs nicely better than baseline bag of words or canonical correlation analysis models. This theme of wanting to exploit recursive structure in neural network models is something that's been a main focus of my group. I should mention that it's still an issue that is being debated and researched in different ways. So just recently at ICML 2014, people at Google produced a model which it does provide a representation of sentences or paragraphs of text, but it's a completely flat representation that doesn't have any compositional structure that works out sentence meanings. But nevertheless, they were able to get some very good results from that, which beat out some of the results we had previously published on sentiment analysis. But nevertheless, fundamentally, I don't believe this is right, that sentences have compositional structure where parts go in to build the meanings of bigger parts, and eventually good models will want to model that. And you can see that in many places. Here's another piece of work that came from ACL 2014 from Ayer and colleagues. And so they're looking at the task of political ideology detection. And precisely in a different language domain, they're making the exact same point about wanting to find and exploit compositional structure of language. So their point is here that, well, if you have the phrase death tax, that represents a Republican ideology, or its adverse effects on small business, Republican ideology. But then when you take another piece of text like they dubbed it the, well, that's actually neutral in terms of ideology, because that could go either way. But once you then build the bigger constituent of they dubbed it the death tax, well, then using dubbing and then a piece of Republican ideology is then giving you a larger constituent that has progressive ideology. And so we want to represent exactly that kind of structure. That isn't something that only happens with language. I think exactly the same thing will come to be seen to be vital in doing image understanding as well. Because as soon as you have a complex scene, well, it's got the same kind of compositional structure of parts that go together in an understanding of the scene. And when you want to do deeper semantic tasks, so another task that we've worked on is relation extraction, where you're taking pieces of text and are getting out of them particular logical relations. So here we have a relation of a message being about a particular topic. And well, precisely how we're wanting to do this is exploit the compositional structure of the sentence meaning in our neural network to get out these relations. Okay, so I hope I've given you some idea of the general approach here and its importance. What we want to do is to have computers with understanding. And the only feasible way of getting that understanding is to exploit the knowledge that already exists. Now, in the modern world, that's maybe more likely to be Wikipedia pages than actually going to the Trinity College Library, but it's the same language information. And what I've wanted to argue is that for getting out that language information, a central tool we want is being able to easily get out meanings. And some of the tools for getting out meanings that we have is representing meaning similarities in distributed representations, using other representations like dependency representations that most manifestly represent meanings. And so together, tools such as these and others are leading to a new resurgence in computational semantics. And so there's now a lot of exciting work in doing natural language understanding happening in the NLP community. And I think that will lead to new abilities for us to have knowledge that we can use to give us artificial intelligence. Thank you.
Thank you for that inspirational talk. I think while Nima is setting up, we can maybe take one question. Mari?
Hi. I'm curious, one of the things that I've actually been doing with your professor is looking at domain annotation. One of the problems I run into, so one of the problems you run into, is this on?
Press the button. I think the answer is that the implications are good, but that's prospective rather than real. So, I mean, there are two advantages that having distributed representations can give you for parsing. One is that it's very easy to learn word representations in an unsupervised manner. And so that gives a very good angle for having a system that knows a lot more about word meanings and meaning relationships over a vast vocabulary of words, even though our supervised parser training data is small and only knows about a small vocabulary of words. The other big way in which distributed representations have been helping, and I think this is most of the gains that, for example, that BBN machine translation system is getting, is precisely distributed representations because they allow sharing of meaning components, a really good way to combat sparsity. And so for the sort of more detailed probabilities that you're getting as how likely one word is to modify another, even if the word is seen, distributed representations can help. But I haven't actually shown that, and you're, of course, totally right that a lot of our NLP tools work great on well-edited conventional texts and work poorly as soon as you're going into informal texts of various kinds, like discussion forums and Twitter posts and things like that. And there is a lot of work to be done to do that kind of domain adaptation. But I very much do think that distributed representations are a useful tool in doing that.
So in the interest of time, we'll have to hold further questions for later. Let's thank the speaker again. The next speaker is Dong Yu. Dong is going to tell us about the application of some of these methods, neural networks in particular, in speech recognition. Dong is a principal researcher in the Speech and Dialogue research group here at Microsoft, and he's pioneered the use of deep context-dependent neural networks in speech recognition. In the last few years, this has really literally revolutionized the field, and shortly after his initial work, IBM, Google, Amazon, and many academic institutions have all adopted this basic technology. Since then, Dong has shown that neural networks actually learn a language-independent representation of speech and shown how to recognize multiple speakers talking at once. And so today, he's going to tell us something about his journey doing this research and what he's found.
Thank you, Jeff. So over the last several years, we have seen a great improvement in accuracies in speech recognition systems, mostly due to the application of deep neural network to the speech recognition systems. So in 2009, University of Toronto published a paper in NIPS workshop. They showed that if they use deep neural network, they can improve the phoneme recognition on a timid recognition task to 22.4 phoneme error rate. This result is better than the Gaussian mixture model using maximum likelihood training criterion, but worse than the same model trained using sequence descriptive training approach. However, this is something showed promising results because in the past, the neural network hybrid system only can beat the GMM systems trained also using the monophone. And now it can beat systems trained using the triphone system, trained using maximum likelihood training strategy. So in this architecture, they still used the same components used in the early 1990s. The model monophone states using frame discriminative training, often called cross entropy training criterion, and MFCC features. So in 2010, Microsoft researchers started to work to see whether this gain can be carried over to large vocabulary speech recognition. And the first thing they tried is the same thing as before. So basically, we applied this monophone architecture directly to the large vocabulary speech recognition. And it turns out that we observed a similar performance. It's better than the maximum likelihood trained GMM system, but worse than the system trained using sequence discriminant training. So the gain comes when we applied the context-dependent phoneme units as the training the network output nodes in the DNN. And suddenly, the error rate was reduced significantly. As you can see that it's reduced to 30% on this small task. This work didn't generate a lot of impact at that time because the task we used is a voice search internal task, and the training set we used is only 24 hours. So people have argued that whether the same gain can be extended to larger data sets or other tasks. So 1 year later, we published another paper on this, and this time we scaled up these findings and applied this to the switchboard benchmark system. And this time, this task has over 300 hours of training data. And surprisingly, actually, we saw bigger gains on this task than the smaller task we tried before. And you can see that by applying this DN technique, we can actually reduce the error by almost 1/3 compared to the GMM system training using the sequence discriminant training approach. Although at that time, this DNN system is still using the frame cross entropy training criterion. So since then, many work has been done to further improve the deep learning systems for speech recognition. And I will go through some of those improvements I think are most relevant to the task. So the first thing we want to improve is the decoding speed, because otherwise you cannot use this in the real-time systems. And Google published a paper in late 2011, and showing that by just use engineering optimizations, they can reduce the runtime by 20 times. So basically, reduce from 3.89 real-time factors to only 0.21. So this means that the barrier to adopt this technique in the real-time speech recognition system is gone. The second thing we want to improve is the training speed. And many groups have spent lots of effort on that. And in Microsoft, we propose to use a pipelined training algorithm where we can parallelize across 4 GPUs with about 3.3 times speed up. And Google proposed to use ASGD training algorithm across different CPUs and also get great parallelization. But more importantly, later on, IBM and Microsoft both proposed the technique to use low-rank approximation. So originally, you have a very large weight matrix between 2 layers, and you can use singular value decomposition and convert that into 2 smaller matrices, and without lose accuracy. This can cut the both model size and the training and decoding speed. Decoding time by 2/3. Okay. So this is a very significant breakthrough. To further improve the accuracy, different groups have tried to apply the sequence discriminative training technique that has been shown to be successful in GMM. So actually, in the early 2009, IBM already published a paper to show that sequence discriminant training can be done on the neural network hidden marker model hybrid system. Unfortunately, at that time, they are not using deep learning techniques. They have a normal conventional shallow model, and they are not modeling lots of systems at that time. So the performance of their system is worse than the GMM system, but they do show that the sequence discriminant training can significantly reduce the error rate compared to the CE cross entropy training. And almost at the same time, Microsoft also tried to apply these techniques, but we only tried on the timid, and so we didn't see any significant gain. The breakthrough came in 2012 when IBM successfully applied this technique they proposed previously to the CDDN HMM. And they showed that by just doing this, they can further reduce the error rate by about 17%, relatively. And this result of 13.3 is very significant because in the past, even if you use multi-pass decoding or the normalization techniques, adaptation techniques, using GMM, you can only achieve 14.5 word error rate on this task. But now, by just using single pass DN system, and you can already beat it. So from that time on, I think almost all the companies switched to the DN system. In 2013, many groups actually can successfully implement this sequence discriminant training technique. Actually, there are lots of tricks to make it to work, including how you generate lattice, how to compensate lattice to avoid things like a silence frame wrong way, and how to control the overfit, and how to select the training criterion for your task. So lots of work has been also devoted to trying to understand why DNN system actually works. And in 2011, Microsoft researchers have tried to see whether the feature engineering techniques worked before for GMM also works for DNN, and we found out that those techniques helps much more on the shallow models than on the deeper models. And we consider that this is because in the DNN, we jointly learn the feature representation and the log linear model. And so lots of the feature engineering techniques we used before may be reduced or removed. So in 2012, both University of Toronto and Microsoft published results on using log filter bank features instead of MFCC as a feature to the DNN. And they both show better results on timid and larger vocabulary speech recognition. And from that time on, I think almost all the groups no longer use MFCC as a features. They typically just use log filter bank. One criticism to the neural network systems is that it's difficult to do adaptation, and the adaptation quality is bad. And in 2013, we actually showed that at least for some tasks, adaptation can be very effective. For example, in this case, we proposed a KL divergence regularized approach to the adaptation, and we achieve 3 to 20% relative rate on this short message dictation task. Depends on how many utterances you have for the adaptation. Lots of other works has also been shown that you can use a structure like this. Basically, this structure is the same for noise-aware training, speaker code, and speaker-aware training. Basically, you have a separate segment input which models the speaker or noise or something like that. And then you adjust that, you train this or directly derive from your observations, and then use that to offset the bias of your neural network. And you can achieve great adaptation ability. For example, in IBM system, they can reduce the error rate from 14.1 and to 12.4 by just using this speaker-aware training. And a lot of people have also been working to see whether convolutional network can help speech recognition. And this is mainly because in the speech recognition, you still have some structures along the frequency axis. For some tasks, we do see some improvements. For example, in the switchboard or in the voice search, we see some improvements using the CNN. But on some tasks, we don't see any gain. But by combining CNN and the DNN, IBM shows that they can achieve on the switchboard task 10.4% order rate, which I think is the best published result on this task right now. About 30% better than the best possible result you can achieve using GMM system. In the recent years, there are other advancements along the way. For example, many groups have applied the multitask and the transfer learning techniques to the system and apply that to multilingual ASR, low resource language ASR, and multimodal ASR. And University of Toronto and Google also tried to use long short-term memory recurrent network to the ASR. And the rumor said is that Google can achieve additional 10% world error rate reduction by using ASTM. We don't know the exact detail yet because they will publish the paper in September this year. At Microsoft, we have been working on single-channel mixed speech ASR, and we can beat the past best result by a big margin as well on this task. So moving forward, we consider that the closed-talk single-talkers ASR is largely a solved problem. In most commercial systems nowadays, you can achieve more than 90% accuracy. And some companies even consider that their goal is to get 90% sentence accuracy. Okay. So but we still have areas we need work. For example, the far-field microphone recognition is still very bad. When we recognize under very noisy conditions, it's also very bad. When you have many speakers talk at the same time, the performance is also very bad. But some of those tasks may be easily solved if you have enough training data. For example, for the far-field condition, probably you can get significant improvement once you collect enough data for that. But for some tasks, we need some new models to. So we are working to see whether we can build a system that can continuously predict, adapt, and learn. And this requires some new framework, and we are building a new abstract model we call computation network. It's a generalization of the DN, CN, RN, ASTM, and many other architectures like that. And we believe that by applying this kind of models to the speech recognition task, we might be able to advance the state of that further. That's all. Thanks.
And we can take a question. Yes, Chin.
Like a lot of those, you're talking about getting more data in order to train more sophisticated models. But in the case of far-field simulation, how do you get more data? Are you going to collect just realistic data or simulation data?
I think in the earlier development stage, you can use synthesized data. But eventually, you still want to have the real data collected.
So I had a question about essentially bringing the feature extraction all the way to the PCM samples of the speech signal. And I was wondering, have you considered, for example, the ability to just represent the FFT itself with a deep neural network? The FFT, as you know, can be represented with a butterfly network, which requires log-n stages, and maybe one would need like log-n layers to represent it, in which case maybe going drastically deep or devastatingly deep would essentially allow one to not even need Mel frequency or Mel scale filter bank transformation first. It seems like the Mel scaling should be relatively easy, could probably be done with one layer. But it's the FFT really, which might be the challenge. I was wondering if you considered doing that.
Yeah, great question. So IBM already had a paper published to show that you can learn the Mel frequency matrix directly. And we at Microsoft, actually Yasha and Mike and I had an intern project this summer. We are working to see whether we can learn this FFT stuff directly. Well, it's still in the early stage, so we don't know it yet.
Okay, I think we should wrap it up here. Let's thank all the speakers again. And thank you all for coming. I hope you have a sense now of what we sort of think is the frontiers of speech and language.